Alright, yeah. So I realized that I actually made a mistake last time, like in the symmetry stuff. Like, I was, I was, yeah, so like I was looking at the, this transform policy function in the horizontally, this thing right here, and this, like, this whole thing which is in place, just like kind of reordering this, that is really stupid. Because like if you look at policy.ts, right, like that actually does nothing. Like I'm literally like sorting right there, like reverse and sort, like kind of like the same underlying thing where we're just like in place shuffling stuff around, right? Like that is really that doesn't really change anything because we need to like kind of like swap the probabilities, right? Like this is not really doing anything. Like I mean, we have to actually like take like the move in the number. We have to actually swap the number. Like, well, let's just say, like, if you look at our example, right? Like, if you have like a state, like the first, I mean, 0, 1. So like the second column with index 1, like its probability vector is 0, and then like that corresponds to 4, right? Like the whole size minus 1 minus that relationship to like flip it about that, right? Like this formula right here, C prime equals the number of calls minus 1. Yes, minus 1 minus C. That's like the this function. Basically, we can move to the other side, like C plus C prime equals number of calls minus 1. Therefore, it's a symmetric thing. There's symmetry. This is its own inverse, right? Quite understandable. So, like, if this probability, like, if the probability of, like, this is 0, like, if the probability of 0 is, like, P0, like, whatever that is, P0, then, like, in the horizontally flipped policy, P prime, like this 0 goes here, just like how like this 1 goes there, like you flip it about this axis. So like you have to not like this, like my whole reversing thing kind of assumed implicit was my assumption that like the or like the uh the moves in our policy were like ordered in such a way, like either kind of like 0 to 7, whatever, 0 to 5, 0 to 6, like they were ordered in a way such that like you could just reverse them, right? Now, already my thing is wrong because I'm not just like reversing the probabilities, I'm also kind of like reversing the whole move object pair, which is doesn't really do much, right? Like basically, I'll just like I'll just show the fix which I had in mind because like what I'm doing is nothing. So like let's actually just fix it. Get status, get log, yep, get pull. Just make sure there's nothing, no weirdness has happened. Okay, then v symmetry.ts. So this thing right here. Okay, copy is okay. It's always okay to copy something. That is completely fine, right? Now, what we're going to do is just iterate over it, right? Like for let's do a 2 paste for move and prob of for let move and prob of copy, right? Copy p dot move and probabilities. So then for each thing, right? The key idea is that like what we have to do is that we have to like kind of implement this this formula, like num calls minus 1 minus c. Like in fact, I could actually like kind of put that in its own kind of relation just to show how important that is. In fact, that's a good idea. Const horizontally flip column index, right? Which is a function that will take in C a number and returns a number, right? How is it done? So it's like const, then the function name, then this colon to do the type. Its type is a number. It is like a type is a function that takes in that and an arrow sign, and it returns a number. This is very verbose and very duplicative. Like this whole thing, like that, kind of like seems like this. Maybe there's a better way of doing this. Probably is. I mean, I know that like, well, whatever. I think this is pretty much optional. Like it can be inferred from that. So then const horizontally flip column index is a function that takes a number, returns a number, and we shall define it as C number and returns a number. And we just do this. That's it. This thing we just copy from here. We just take that here and let's yoink that. And we return that, and that is it. So then this thing right here would be a that of C, right? Like we just kind of copied, like we pass in C, it goes inside this function, and just returns that, which was originally there. Just like kind of like do a clear get diff that, just to like kind of see what happened. Get diff that. So now like initially this used to be like game state, like it used to be the formula, but now instead we just kind of encapsulate this logic inside this function. So horizontally flip C, so we pass in C and it does the exact same thing it was doing there. But we can now use it in our flip policy horizontally, which we're about to do here. We just take the move and probability and we look at the move and then we like look at its column index and we just do like kind of reset that. I mean, in a sense that makes me a bit uncomfortable because like move's column index is kind of like, it's like a private, I mean, I guess it's public, but like it's kind of like private to me almost. Like, sure, I can define a getter and a setter and then like kind of make it private and then set it. But anyways, yeah, let's just do this. In fact, let me just bring up move.ts. So then like, let's go to the bottom of the page. So right here, what you want to do is we want to get the move. So move and prob 0 to extract the move, right? And then you want to set its like column index. Let me just, that's why I opened that file. Move.column index, right? Move.column index equals, and then that's like kind of the exact idea why we have this function right here, right? You join that, and we want to like copy it right there, right? Like that. That's it. And this should flip the policy horizontally. I think that's sufficient. I believe that last, and that's much more readable. I mean, that's much more terse. I mean, that's just, yeah, I think that's it. So let's just kind of like, let's just work through an example and actually connect for. Let's just like say that, right? Let's say that like we have, so connect for is a 7 columns, 0, 1, 2, 3, 4, 5, and 6. Now let's say that like in the actual like kind of thing, let's say that column 2 is completely filled up. Column 4 is completely filled up, right? And then like our policy would be kind of like, let's just say like everything is like kind of like, let's say that like 3 is like, let's just say 1, 2, 3, 4, 5. Okay, let's say that let's say 3 is also completely filled up, right? Actually, no, let's not say that. Let's say that I don't know, 0 is completely filled up too. So we have 1, 2. So let's say that we have like 40% chance of putting it in column 3. Then I don't know, 30% chance, 20% chance, because I know a 4 plus 3 plus 2 plus 1 lines up to 10. So that, right? Let's say this is our this will be our policy right here. This is our policy. we drop it in column 1 with 30% chance, column 3, 40% chance, column 5, 20% chance, column 6, 10% chance, right? And when we flip it, right, once we do the flip, then like 0, 1, 2, 3, 4, 5, 6, right? So now let's look at the fill. So if 0 was completely filled, then its complement, if we pass that into like this function here, right? Num calls is 7 calls, minus 1 is 6, minus c. So 6 minus c, that's what this function does. It returns 6 minus c. So 6 minus 0, 6 minus 0 is 6. That means that like this being full maps to this one being full. Quite straightforward, right? What about 2? Again, if we kind of like draw like a vertical line, it would correspond to the 3's column, because 6 minus 3 is itself, right? Like we flip about that vertical line right there. That's kind of like the idea. So 0, 6, okay, then 2, well, clearly like it's like 1, 2 from here, so 1, 2. And that's filled, right? Like 0 filled, then you go 2 this way, so it's 2 that way. Like in different ways, like sweeping right then sweeping left. And same thing there. Like you start off at the end, and then you kind of skip it to make it full. And what do you know? Like 0, like 0, 6. They're complements, because 0 plus 6 is 6. 2 becomes 4 complements. 4 plus 2 plus 4, and 4 plus 2 are 6. Okay. So now, like, we really want to drop it in 3, right? Well, 3 flipped, it becomes itself, so like that kind of stays the same. So like we're basically kind of transforming this move, like kind of matches this one right here. That's kind of like the complement. Now let's say this is the most desired, like we most likely want to place in column 3. Now here we least likely want to place it in column 6. Well, what is that, right? What is that? Well, that corresponds to this one. So now we really don't want to place it here, right? So this one pretty much is a no-op, right? But this one, like this move, saying, hey, let's take the last column and let's really make the undesirable. But in the horizontally flipped version, it's to take the first one and make it very undesirable. And then these dashed ones, these filled ones are omitted. They're not in the policy. They're illegal moves. So for this one, there's not much to be said. It's just identity, right? But for this one, to go from here to here, we do 6 minus 6, that equals 0. So like we can just kind of take the column index and just kind of like map 6, make 6 to 0, like passing it into like our trusty old function, which is 6 minus c. 6 minus 6 is 0, checks out. 6 minus 3 is 3, checks out. What about this one? This one is a 0.2, so it's like the second. It's like that's the least favorite, and this is the second least. And this one kind of corresponds to this one, like 5 and 1, right? This one is a 0.2. And that one kind of maps from this one. That's its complement, right? 5 plus 1 is 6. They're complements. And same for this one. Same for that one too, right? This one will obviously map to 5 with 0.3. So if you look at like these kind of 4 arrows, like these 4 connectors, like let's take this one, any of these 4, like 3 minus 3, 5 plus 1. So like that's kind of the ideal. We can just take the move itself and just swap its, like flip its column index to do 6 minus. I keep doing this is like the stupidest one. Let's take this one, right? 1. So then to go from here to make it that, we just do 6 minus 1 equals 5. That's it. So I believe that like this is the correct way to I believe like I just kind of fixed this function. So now it should be correct, I think. And again, we can pass them both because it's its own inverse, so that's kind of fine. Okay, Claire, get diff. So now we just kind of like are very kind of we're getting very like we're just really spelling it all out, right? We're just writing this function, we're enshrining it, like giving its own like function that does this operation. So we just kind of like pass it in there. Okay, that's a no-op. And then from here, rather than in place reversing, the whole point is that like reversing this whole pair is really stupid because that's not really doing anything, right? Like what we want to do is we want to actually like this move and prob changes, right? And specifically, like the probability of like a move becomes a probability of its complement. Like if we want to like with some like we have P of C, that's the prob for column C. That becomes that same prob. Let's let like X equal to P of C, right? So in a rotated policy, which prob would X go in? I mean, which column would X be for? Well, that's C prime, 6 minus C. So that's what we exactly do here. We set its like this is move and prob. We're changing the column index, so we're changing our move index to like become for a different column, particularly the column that's reflected about the vertical middle line. I mean, I already talked about this. Like I showed why it works. So that's it. I think this is correct. But I mean, I was so confident last time, and like that was clearly wrong. So yeah. Status. Let's. This looks good to me. Get status. Get commit. Hopefully fix flip policy. Just copy it. Get status. Get push. Okay, this looks good. Yep, we define this. Yep, this is the correct commit. Okay, that works. Okay, so now let's actually use our symmetries, right? Get status. I mentioned that this is missing one thing. It's not just like when it reaches the leaf node, but also when we're training it. Like we train it, like we generate, like we kind of expand the data when we're training. If we have like K training examples and like if we flip them all horizontally, we get 2 K training examples. Okay, so let's do this one particularly, right? Right. Okay, so let's do that. So it's like create node, right? So right here, right? Oh wait. Okay, so the first, so this is the base case for terminal, and that should be unchanged. But this is the key thing right here. When we're actually calling get policy and value, right? So right here, we could take the game state, or we can take in a reflected version of it, right? Like this. When reaching leaf mode, the current URL is called with the reflector rotate version of the board to exploit the symmetry, right? So like, we should take a random symmetry then, right? Like, if you go here, right? At the end, we have like symmetries. Export const symmetries. Okay, we have to actually like define. Let's do the imports. And that is the const is called symmetries. Symmetries. And we have to also do something like this. Wait, what? So yeah, symmetry.ts. And same thing from there, right? Like we're getting the class name symmetry, like we're the symmetry class, and then our list of all the symmetries, particular identity and horizontally flipped, right? Okay, great. So now, we're right here, right? And policy and value. So now let's like get a random symmetry, right? Or wait, no, I was using draw. I was like, what? Let symmetry equals to, and what's that like kind of technique for doing a random stuff? Again, back to my old commit. I think it's called integrate. Wait, no, I actually have it in this file, right? When I'm like doing tie breaks and the best at UCB score, random. Copy this line. 105 is about the same line. Something like this, right? Oops. Symmetries, GG. Symmetries are a list of 2, right? Symmetries. And then, so symmetries, mat.random times symmetries.length. So we're randomly choosing a symmetry from the symmetries, right? So again, mat.random gives you a result between 0 inclusive and 1 excluded, like 0 and 1. We multiply it by 2 because symmetries is 2. It's particularly it is these two, identity and flip horizontally. Those are the 2 symmetries we defined. So then when we do mat.random, gives us between 0 and 1, multiply by 2, so now we're between 0 and 2, where 0 is inclusive and then 2 cannot be reached. So when we truncate it from mat.floor, we get like kind of something that could either be 0 or 1. It cannot quite be 2. So if mat.random was like between 0 and 0.5, we, by doubling it, we get 0 to 0.99, like 0 to 1. And then if it falls in the second bucket from 0.5 to 1, then when we double it, we get 1 to 2, 1 to 1.99, because it'd never be 2. So the end result is like, that like this randomly choose an number between. And we already talked about this. So it's, I mean, yeah, this is just how, so again, like 0 to 0.5 becomes 0 to 1 when we double it. And then that would, when we truncate that, that basically gets us to 0, which is the first symmetry. Symmetry is a 0. And if it landed from 0.5 to 1, I'm going to say its symmetry is a 1, because like 0.5 to 1, when we double it, becomes 1 to 2, but it can never reach 2 because mat.random, like the 1 is exclusive. So it's like, it's basically 1 point whatever, not quite till 2. So then when we mat.truncate it, we get 1. That symmetry is a 1. So thus, like, we have 50% chance of getting either one. So it's like hopefully random, assuming mat.random is correct. So you have our symmetry, right? Now what we want to do is we want to like get the Polystone value for the symmetry game state, right? So let's look at the methods that like, so symmetry has like symmetry dot like 18, right? We have like this function right here, transform game state, right? So what we do is we take the symmetry so you have symmetry transform game state, right? So that's the idea. So this is the policy and value. This is a policy and value, right? But like, and that's normal. But now what we have to do is we have to like kind of do policy equals, and then like the same exact things, try to transform, inverse transform, but like when we restore it, right? So the policy which we have right now technically is a policy of, the point is that we have to do we have to like swap it again. That's kind of like the whole idea behind this. I mentioned this last time or time before, sometime in the recent past. So like we have like kind of like, so like we're given like S prime and P prime, right? Like our neural network kind of gives us like we passed in S prime, right? Like we passed in like in our like what we did, we called get value and get policy and value on transform. So this gives us S prime. And when like from S prime we get like V prime. Well, V prime and V are the same. We get like P prime, right? Like if we go here, right? Like this is our state. This is how our state looks. And if we pass it a neural network, we get like this one right here. We say, hey, we really should put it in column 3. But then by flipping it, now like if our neural network is a good understanding, like strong neural network for a policy, it should give us a 1 in column 2. Like, hey, we really need to block this other player from creating an unstoppable double attack threat. And then like, so then this is the policy we get, 0, 0, 1, 0, 0, 0. Like that's like the policy which we get. 1 for 100% chance for like a strong recommendation on column 2. But then column 2 is not column 3, so like we have to flip it back, and that's the inverse. And that's like the whole motivation behind this function right here, right? Goes from P prime to P, right? So we have to copy that. I mean, these are about the same, but yeah. So symmetry dot that. The transfer inverse policy, and that is policy and value of this one. Right there. Okay, so let's recap the changes. Like that's it. Like just like 3 lines of change. Just like this, and that. Like introduce this new line. Policy and value, like do it, but for the symmetric. Let me be particular about that. Policy and value for symmetric state, right? And then the policy for the original state is we take the policy that we got for the symmetric state. We have to like propagate that. Propagate the name change. Like that. Perfect. So like the policy is for our state, just this game state. But then we kind of transformed it first to like some symmetric state. Like we got P prime and V. Now the value is just like, I mean, the value like, so like the value for the symmetric state is the same as the value for the state. Like again, like the outcome for like this and this, like it's the same thing. Like you can just like flip the board, like look at it differently, but like if you're like left to right, right to left, but that doesn't actually change the relative positions of the coins like to each other. Like it's just a difference in like, I mean, it doesn't change the outcome of the game. Like it's still the same game, same evaluation. Therefore, like the value we can just extract, but this policy we had to reverse, or we did have to like take and like flip. And that's what this does. It takes us back from P prime to P. So this looks good. Let's save that. And that's it. We proceed, we'll let everything proceed as normal. So I think that's it, right? Clear, get diff. So in our Monte Carlo tree search, what happens is we take in the symmetry class definition, and then we import like the symmetries, and then we add this new line here. We just randomly choose a symmetry, and then policy and value. I renamed it policy and value for symmetric game state because we're calling like get policy and values again. It's from our neural network. Get policy from the network. It's basically neural network.pred, right? Predict, which is right here, neural net.predict. That like predict, like it's like neural network.predict gives you the P and the V, right? And that is exactly get the P and the V. So policy and value, right? So then you have the policy and value, but we're specifying that it's not from the original state, but rather it's from some symmetric state, or the symmetry we chose was pretty much randomly chosen. Like we fairly picked a random symmetry to choose. So then we just like chose it kind of randomly, to get our policy and value, but it's for the this symmetric state, right? So we have like the symmetric policy and value. The value, of course, is the same, and the policy we do have to like flip it back, and that's why we're transforming it back. And now we're kind of back to policy and value, not for the symmetric state S prime, but just S, the original game state. And then like just like we had there, and then we can just proceed as we were. So that should be it. Get at all, get status, get. Okay, well let's first make sure this runs, right? It's like TSC, like that. Good. There's no like compile errors. So get status, get commit, leverage or use symmetries. Use gonna copy that. Use symmetries and create a node, the Monte Carlo leaf node. Use symmetries and create node. Okay, so this change, so then this change is symmetry. We randomly chose symmetry, and then we kind of transformed it. The value evaluation is the same, obviously, but the and the policy okay, so when we do symmetry to transform game state, we're basically kind of like going from this to this. So like the same colors get preserved. So the image stack, like it would look like kind of like this, and like that would become the image stack, like here. And when we transform it, then the image stack should look like this, and then that. Where like these two get flipped to that, and then those two get flipped to that. Now, is that what happens? Like in each RC, we kind of like do this formula right here. Like the R's, whatever's in the R is the same, but then these are flipped. Okay, I think that's correct. Yep. So like this, the neural, like yeah. In fact, we can have kind of like. In fact, it's so nice that I drew this like right on top of that, where like that's S, and that's like S prime, but like encoded like into a okay, this line gets really annoying. Let's kind of delete that line. Okay, yeah, but like it's kind of like a nice nice little like kind of visualization of the like the inputs in the neural network, how from S to S prime like encoded into a tensor for our input. Okay, yeah, okay, I think I'm comfortable with that. Get status, get push, done. So we're doing 1/2, like the symmetry like that we've done, we have taken care of this. It's invariant to rotation reflection when MCS leaves which is a leaf node, which is create node. The current neural network is called the reflector rotated version of the board. So we kind of like took symmetry and then kind of applied symmetry's transform to get S prime, which is the reflected version of the board to exploit the symmetry. And we extended it to connect forward. And we can do the same for BumperCoins, where it's not just flip horizontally, but BumperCoins also has a flip vertically. Like Connect 4 doesn't, because of gravity, all the coins fall down. We can't just like inverse gravity like that. That would fundamentally change the game state. So like it won't be the same anymore. It's just they only have flip horizontally. Whereas BumperCoins is flip vertically too. There is no rotation because it's not a square board. Yes. Oh yeah, we can also kind of composite flip horizontally and flip, like you can do a composite operation of flip horizontally, parenthesis, like, and then like we first flip vertically, then we flip horizontally, and the vice versa. But I do think that those both work out to be the same thing. Like flip horizontally and then flip vertically, or flip vertically and flip horizontally. I don't think the order matters. I do think that like that would result in the same thing. Like, I mean, I'll have to think about it. Maybe I'll have to like work that out. But the point is that at least for C4, the flip horizontally is very, very straightforward. This transformation of flipping by using this like very nice formula right here. C prime, like that C prime C plus C prime is number of commas minus 1. That's a very nice relation that we've derived. Okay. So then that's done. And again, when we train it, we have to use symmetries too. But then that's that training into symmetries comes in this line. So now I guess it's time to actually like do this. Actually do the policy iteration, like do the self-play. And then once we do that and we like run that, execute a bunch of self-plays, SP self-play, then yeah, self-policy iteration, SP self-play, then we're finished. So that's it. Just one more TypeScript file left. Let's call it train.ts to train. And then we'll be done. Believe it or not, we have all the elements required to train our unsupervised game playing agent. Let's solve a central policy iteration algorithm. Okay, we play games, compute Q values using our current policy. Then update our policies and computed statistics. Okay. Yeah, these Q values are stored in the edges. Here's a complete train. We initialize your random weights. We put in our game self-play. And each turn of this init we initialize, we have to also load it. In each turn of the game, we perform a fixed number of MCTS simulations. Starting from the current state S of t, we pick a move by sampling from the improved policy. And then the reward is filled in the end of the game. Wins or -1, the search tree is preserved during a game. The iteration network chain that obtains, and again, we do symmetries here too. And this whole if statement we can ignore. Again, like I'm saying, we're ignoring these three, where we're not going to actually like implement them. So magically, and it improves almost every iteration, learns to play the game better. That's it. This is all. That's it. So I think, well, I mean, the main thing I did is just now is just like hopefully fix this flip horizontal. I think that's kind of the key thing for the time being. And I guess like the next thing to do, I'm not sure if I'll do it today, I might just start, is just kind of implement this execute episode just to generate the training examples. In the future, we will actually, you know, do the training. And that's where we, again, use symmetries to generate more training data. Yeah. $4.23. Okay. So execute episodes. We have a starting game state. And we just like, this is do MCTS, which I defined. And then we get our policy. From do MCTS returns the policy, and then we just kind of sample it, right? Sample from improved. Okay, so this notation's a bit weird, but the point is you have to sample it. So we do Monte Carlo tree search, and then we get our improved policy, and then we randomly choose the action from it, and then we you know, apply that action, apply move, and we keep repeating that. Okay. So many files. Let's create train.ts, which is not a class but a script. This this file for self play to train our, or, oh yeah, I can't speak English. Train our model via self-play. Let's open that and open mcts.ts. Okay. So right here we have like kind of function search. Let's copy that there and let's have a function self-play game, which is going to be like, I'm calling self-play game. It'll basically be my version of execute episode. Play a single game. Self-play sing game. Okay, so what we need in this game is take in the model and then just void. Self-play game, which takes in the model. Okay, so then examples. Okay, so like we have kind of like an examples. State policy. In fact, I can just kind of create that and then like here. So model is that. Let's actually create like a little like interface, or how do you do that? I want to like create like something like kind of like this. TypeScript tuple custom tuple type. Tuple class. Names tuples, tuples. TypeScript. Oh, I could have done this for policy, right? For policy, just like the move, a number, and then the whole thing as an array, like another one. But okay, let's just do that then. Let's see what's happening here. Run. Whatever, I'll just kind of copy that, right? Paste it here. So now our type for a type, let's call this type example, right? let's define example. So example is a training example, right? Like it is a SP, like it's this tuple here, the state, the policy, and the reward, right? We need to kind of create that type. Examples assign rewards, like the whole thing. Like examples has like this tuple right here, the state, so this tuple is like it takes in the game state, or yeah, game state, and then it takes in a policy, and it takes a number for reward, like that. There's no colon there. Okay, cool. So we need to import those definitions. We need to take in a game state. And we need to take in a policy. A number, no need for that. And then we need to import the tf.layers model. We need tf. Okay, great. So self-play game, right? And we have our example type, right? So let's pass in our examples. Examples, which is an array of example. And then key part of file. This function plays out a single game via self play. And generates and has side effect of appending onto examples argument the training examples generated in this game, generated by playing this game. Okay, that looks like a nice comment, just explaining everything. So that's like the key thing, like to self-play the game, right? Okay. So let's kind of open up our game.ts, which kind of like, and then let's open up everything. Just like that's too many TS files. Train.ts, game.ts, gamestate.ts, and so forth. So game state is new game state. That's it. Like this. Let's kind of copy this line. Let game state equal to our new game state. Can get rid of that. Get rid of this. Get rid of that. Get rid of this. What's this question? Let's get rid of that. Let's leave this tab open. Kind of go back here and refresh for commits. Okay, so then first we already have examples in our parameter. We have a starting game state, and then what? Okay, so it's kind of like while that, right? Like a while game state dot get game status, I think. Dot get game status. Dot get game status equals to the game status. Equals game status dot, and then dot what? Dot ongoing. So while the game is still ongoing. So while the game is still ongoing, what do we do? Well, we do MCTS, right? Oh, we have to also import game status. So while the game status is still ongoing, what we want to do is we want to like kind of do this. Let's export this, right? Export function do MCTS, right? Do MCTS. MCTS. Do MCTS, right? Do MCTS from MCTS. Again, see like mcts.ts I'm highlighting right here. The file name, mcts, and the function name do MCTS. So that takes in the game state and the model and returns a policy. And that like kind of does whole MCTS a whole bunch of times to like kind of like every single iteration of the search, we're adding one more leaf node onto our kind of our root, our tree. Like we're building a tree starting with the root, and then we kind of add like every single like iteration of search, we kind of go down the tree and we just kind of add one more leaf node. And like we keep doing this for like, I think 100 times or 200, whatever. This constant was defined at the top of this file. And then like we from that we kind of like normalize, like we get our new policy and just sample from that. Okay, so we have to do that, right? Do MCTS. So sure, we can do that, right? Let's copy this whole line actually. Okay, so then let policy equals to do MCTS on the game state. And the model, right? That's it. Do MCTS takes in the game state and the model. And then what we need, so now we have like our MCTS.py, right? So then what we're gonna do, actually, wait, no. Let's like kind of build in, actually, let's do what they do. Let's actually, let's actually return the example. Let's return in an example, an array of examples. And returns training example generated by playing this game. So then let examples equal to a new thing right there, right? So we have the policy. We have to do examples dot push. We have to append onto examples three things. Oh, this is crucial. Game state dot clone. Very critical that we clone it. It is extremely important to clone our example. Like S, like you see how we have like S mcts.py, the policy which we got, and then for now let's make that 0, right? If it's a draw, then great, we leave it. If not, then we assign the rewards, like 1 plus or minus 1, depending on whose turn it is in the outcome. But this S, like you see how S changes right here, like it gets mutated. So we have to clone it to like get a copy. Very crucial. Like it would be such a dumb thing if like we don't clone it, because then like it's just one object and everything points to the same object, and like that is painful to think about. So we have to clone it. A bug that could be such a painful bug. It's important to clone these things. So the example takes in game state and policy. In fact, for good measure, let's just do policy.clone, just because I like to clone things. Like, it's very nice to be safe and clone, and then number 0, because well, let's just leave it as default. And in the future, at the end, when we're doing assign rewards, if the game outcome is a draw, then we're done. But if not, then again, like pluses 1s and minuses 1s, plus or minus 1 accordingly. Like this whole thing right here, right? Filled in at the end of the game, right? If it's 0, if it's a draw 0, then we're already done. Okay, great. Great. So that's our examples. And then we have to like get our move, right? The sample move from policy. In fact, yeah, like we're right here. This thing right here, right? Sample action from improved policy. We have to do that. Sample action from improved policy. Okay. I remember like thinking just a few minutes ago, like we could have had like type policy and like we didn't need to file for policy, but I guess I can finally justify it. I'm glad I can justify it because I can like put the sampling thing as a method in our policy class. So let's like this whole thing about sampling, let's kind of call it like sample move, right? In policy. So like the policy.ts, right? So basically what I want to say is we want to have something like this. Sample move returns a move like that. Selects a move or samples a move. Samples a move respecting the probs. Respecting the probs. Respecting the moves apostrophe after the s, prov plural. Okay, that looks good. In fact, there's a leak code question like this. But anyways, let me just kind of go back. So we took the policy which we got from the MCTS from this game state. Then we kind of got a policy. We're kind of like storing this into our examples. Then we're gonna like take our move, right? So like let move to play move. Again, this must be a legal move because do MCTS only gives us legal moves, right? Does it? MCTS? Because like, yeah, because like when it calls create node in the root, like the first line in do MCTS is to create the move, right? And then that like create move like kind of calls a neural network, and then like in the net.ts like get policy and move, I think like there's like a filter for only filtering out legal moves. So move to play move, we know it's a legal move, and that is like we get that from our policy dot sample move. Like that. And then what we do is like we just apply it, right? Game. What's this apply move? Yep, game state dot apply move line 55. Like that, right? So let's kind of copy that. Here, game state dot apply move. Just make sure it does what we want it to do. Apply move. Again, very crucial. At the end of game state, this line happens. It toggles a turn. So apply move just how does apply move work? Should not see this message. Okay, fine. Get legal moves. At least make sure that get legal moves like kind of uses the is P1's turn to make sure the move's turn is correct. Yep, is P1 turn. Perfect. So apply move, what it does is it just kind of goes at the bottom. Wait, no. R equals 0. So while it's vacant, we just kind of keep like we just kind of go start from the top from 0 and like we keep like kind of checking it's vacant and then advancing. Does this move illegal move because it's like kind of topped up and then okay, yeah, that looks good. That looks correct. So game state apply move advances the move, and then we're done, right? We're done. We finished one iteration of this, right? So we applied the move, and then like it's kind of ongoing until at the end, right? So now, if game state dot get stat. So if the game state equals a draw, like we know it's not ongoing anymore, draw, then that's the happy case because we already have 0 in our examples. Then we just return examples, or else let's just have a to-do assign rewards. I'm gonna use the restroom right now. Okay, so while I was in the restroom, I figured out how to do this. It's really straightforward. Boolean, or let p11, which is just a boolean, right? Equals to this. The game status equals status dot what was it called? P11, like that. So if that is there, right? So then like P11 is a boolean. Wait, we're missing the we're missing that thing. Okay, so P11 is a boolean, right? Then like for let example of examples, right? So then like let the reward number equals to something, right? We're gonna figure that out. And then example, right? So example is that example of 0, 1, 2. Example of 2 equals reward, right? So our reward, right, is the same. So like is the same thing. Like if the game state, right, the game state like there. So if the game state has a what's it called is P1 turn, I think. Or I have to write it. Save this file first, then go there. Game state dot like is P1 turn, right? If that aligns with a player 1 so let's say like this is true, right? So it is for player 1's turn is true, and then let's say player 1 wins. Then that means that game state, like the evaluation for that, its value is +1, because the current player whose turn it is, player 1, wins. So we just kind of compare those two booleans. Let's copy that right there. Is P1 turn? If the example of 0, which is example of 0 to get the game state, right? And if that one's is player 1 turn, if it's for player 1 to move, if it's player 1's turn, equals P1 1, right? If this is true, then we give it a 1, or else we give it a -1, like that. That's it. I think that's correct. Okay, let's say that this P1 1 is false. So like the game is over and player 2 wins. And then let's say that the example, so this is false, player 2 wins, so player 1 1 is false. Now let's say that like this is true. So the game state is for like player 1's turn. But this is false. So this is true and that is false. So then we get -1, which means that like if the states are for player 1 to move, then but player 2 wins, that means player 1 loses. That means the value of that state is -1. So that checks out. Right? Okay, I think that's sufficient. Let's save that. And then all that's left now, I think, of course, like this is like kind of like the heart of it, like self-play. All that's left to implement is this thing right here, policy.sample moves, which again, I totally said, like, reminds you of a leak code question, right? Policy.sample move, right? It's called like random pick with weight or something, I think is the leak code, is like the leak code question name. But yeah, just sample the move. So let's implement that. Or I kind of feel tired. Should I just call it a day? Do that later. I mean, it's a really simple thing, but I'm getting pretty tired. Let's see. Sample move. Returns a move representing the moves. Samples a move respecting the moves. Probs. Okay, put a leak code, I guess. Oh, I'm not signed in. Oh, I don't want to sign in right now, actually. Random weight. Random pick with weight. Sure, why not? You need to log in, sign to run or submit. I mean, I know what you do. You just like kind of like to solve this question. Like here, I'll defer this to tomorrow. But like, what I will do before signing off is just kind of showing how you do it, right? Let's say you have like these 4 moves, right? Like point 4 point. Like so you have like move 1, which is a 40% chance, or 0.4, 40% chance. You have move 2, which is like 30% chance. You have move 3, which is a 20% chance. And you have move 4, which is 10% chance, right? Then like, if everything were uniform, if they're all 25% chances, you could just randomly like do the random technique where you pick between 0 and 1 multiplied by 4. And then just like kind of truncate that down and like floor that, and then you're done. But then here, like, this takes up more space. We can kind of like view it visually, right? As like kind of like this, like kind of 1, 2, like kind of like this. You need like 10. Like, let's use this grid. So actually, this is kind of like, can we just zoom in or out? Like this. Let's kind of zoom more out, or sorry, zoom more in, right? Oh wait, what? These squares don't change. Like here, like kind of like 1, 2, 3, 4, 5. I'm taking 5 squares, right? Each one will be broke like 1, 2, 3, 4, 5. Each one will be broken here, right? Like that, right? So now we have 10. We have like 10, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then like here's 0.4, right? So it's like if like this is gonna be 0 and this is gonna be 1, right? Then the idea is that like we kind of like randomly pick between 0 and 1, and then like kind of like 1, 2, 3, 4. So like if this is for 0.4, like this kind of corresponds to 1 and has kind of like 0.4. 0.4 is our kind of like our endpoint, right? And then kind of here is like kind of for 0.3, right? It's like 1, 2, 3. So like if you land here, so this is like kind of between like 0 to 4 is kind of our bins, like if it's like kind of exclusive, and like kind of like this. Like typically in like math.random is like math.random gives you like between like that's kind of exclusive and this one's inclusive. Like can give you 0, but can only give you like 0.999, but can never give you 1. That's like kind of how it works. So like kind of this is like kind of like the bins and buckets, right? Like these are like the buckets. Like this 0 to 0.4 is a bucket for that. And then the bucket for like 2, right? The next one is going to be 30% chance, right? So here it'll be like kind of like 0.4. Again, like 0.4 is like kind of exclusive here, inclusive there. To what? Well, 0.4 plus 0.3 is 0.4 to 0.7, right? And then this one, like for 2, for like 3, like that, right? Is 0.7 to 0.9. And then the last one is just 4, and its range is from, oh wait, this should be sorry about that. Delete this one. This is rounded. Okay, that was terrible. This one is 0.9 inclusive to 1 exclusive. So like basically like this 4 we just kind of got here, and this 7 is like it's a prefix sum basically. That's it, a prefix sum. Like we just kind of do that, and then 1, which is kind of like, so like we kind of like can just do prefix sums. Then we just kind of like go from left to right and like kind of figure out, like we just choose a number between 0 and 1 randomly, and we find out like which bucket this falls in. We can like check off them left to right until we find out like so like that's it. But yeah, like this kind of key idea right here is how I would solve this question. And I have done it before. Like I definitely have. Like here's my profile. I've done 600 and I've done almost 20%, like 602 questions. Is there a way for me to start? Well, the point is like you just do like prefix array. Like we just sum it all up. The key idea is to like break this into buckets and then do it. So like if we kind of randomly pick, like we figure out which bucket it falls in. So like most likely if you pick like 4 million, or if you pick like 1 million random numbers, then like 400,000 of them would be like fall into this bucket. So like 40% of them would be like for move number 1. And like that's kind of like that's like the approach. Like we use this technique of like these buckets and like kind of prefix sums to implement sample move. That's what I will do later. I mean, the concept's really easy. Like this is not a big deal. And like once this is done, once this is finished, right? Once this is finished, we have self-play game that generates the examples. And then actually I'll comment that. Example. This type is a named tuple that represents a training sample in the form state policy reward slash outcome. Yeah, just reward. We know what reward means. Is represent the training sample of represent the training form state policy reward. Okay, yeah, that looks good. So self-play game, like while the game is not over, we just kind of like do Monte Carlo tree search on the game state to get a refined policy. And then we kind of put that, like we kind of take the game state and the policy, and then for now just dummy 0. Like if it's a draw, then like 0 is correct. But like we kind of like stash that quickly in our examples. And then we use the policy, like we're going to sample it, which I'll do tomorrow. Well, not tomorrow, just whenever next stream. Could be tomorrow, could be not. But like move to play. And then we just do game state.apply on the move. And then that transitions us to the next game state. And the player's turn is flips. Like I verified that just now and applying just like a few, like on stream, like recently. I remember like looking at the last line, which I mentioned like toggles it. So then like we keep removing until eventually, like by applying the last move, the game ends. It's no longer ongoing. Either it's drawn or someone won. So if it's a draw, then we should return it, or else we just assign them based on like if their turn lines up with if they won or not. And if that matches, that means like if player 2's turn and player 1 did not win, so player 2 won, then we'd give them +1 or else -1. There are no zeros because it's decisive. If there's a winner for +1, his opponent gets -1. Just the way the world works if it's not drawn. And then example 2 becomes reward. Now let's see if this compiles. Well, actually no, I have to first like kind of let's just do a dummy sample move. Just say like true and then like -1, or for good measure false -1. The Boolean is like whose turn it is, and the -1 is the column number. So that's kind of it. Let's see if that compiles. Just wanted to see if it compiles right now. So there's a mistake. Line 19, comma expected. Oh, I need a closing bracket. Okay. For yours. We import move, and then we import, oh, drawn. Okay, sure, fair enough. We pause the attitude. Let's copy the lead code link for now. Okay. Get status, clear, make sure everything runs. Shall I do run.sh? Move. What the hell? Just want to leave. Oh, move to play. Okay, compiles. Status. Get diff. So get diff, I command here, do mcts, I just added the export word, that's it. And then I'm kind of doing that. Oh, and I have to actually add the train.ts to see it because it's untracked. Get diff staged. Add the export, add sample move, which it's the stub for now, just to like, yeah, that's kind of the idea. And then, oh, I can also add argmax actually, and then kind of call that in game. Actually, yeah, I should do that. Okay, I'll anyways, and for now, let's leave this as added. And then train.ts like this. We just like train our model by self-play, and this is like untested. It's like self-play games, like the heart of the file. Yeah, so actually, like, I'll add that comment too. I was just talking about it in policy, right? How does it use again? In like, I think in bot.ts? Bot.ts, right? Like here, we have like 0, 0. Yeah, so let's actually skip that. Instead of 0, 0, what I should do is like, so that like leverages the fact that it's sort. Let's skip the sort, right? Let's just forget that. Let's forget the sort. Like this whole sorting nonsense, this whole business right here, let's just comment this off. And what we can do is like how we have sample move, what we'll do is like 2yy, right? Or 3yy. Like paste that there. It's a get highest prob move, like the argmax. Get highest prob move. And then what we do here is like kind of get highest prob move, right? Let's see, yank that. And then what we want to do is we want to do let's kind of comment everything off. Return policy dot get highest prob move, like that, right? Okay. I think MCTS does this, right? Like this kind of like, and then what about tie breaks? Okay, something like this, right? Let's copy these 3 lines. For move and prob, let max prob equals to, I don't know, like negative number, -1. For move and prob, let prob number equal to that, about 1, right? If prob greater than, actually, let's just randomly do tie breaks too. Let top moves, or yeah, moves, which is and this one is a number, and let's arbitrarily do tie breaks, which is an array of moves. So if prob is less than max prob, we just continue. So if prob equals that, if prob equals max probs, then we do moves dot push. Yeah, let move equals to the move. So then moves dot push move, right? And then else, that means we must be greater than. Then and at the end of it, we have to set the max prob, right? Max prob equals our new prob, right? Because either if prob is less, or it's equal, or prob is greater than. So that means we have to reset it. And then moves equals, but we have to add the move. We did the same thing in like Monte Carlo tree search. Oops. Shift P. Okay. And then what we do at the end, after all of this, after all is said and done, right? Return the math.random, like the whole thing right there, right? Just copy this now. Let's copy this. And that, right? Buffer moves. Map.floor, random, and then moves. We have to index it, right? Dot length. Oh, what? That's the index, right? That's the index. That's the index of it. The index moves. Okay, that should be correct, right? Max prob -1, list 0. Then for move and prob, the prob number equal move and prob of 1. If the prob is less than that, then there's no point in bothering. But now that we're here, that means, hey, it's a contender. The move is a contender. Let's unbox the move. If it's equal to, we just kind of add it on, and then else. I'm not sure this will ever be hit. Or else, well, who cares? Else, what we do is we reassign the prob, and then we kind of add a new list of just a single element, which is just the move itself, which is now our most promising, our highest likely move, highest prob move. It's just that. At the end, we just like randomly sample, uniformly choose from these moves. Map moves, and the index is like the floor. We truncate that down to the random times move length. Yep, that looks good. Status, declare, get diff. Right, so now like rather than like sorting, we kind of remove this whole sort thing. Right? Like who needs a sort? We just all we care about is the highest move, and then we kind of add this method to our policy. Okay, let's see if it compiles. Good. Let's make sure like the run.sh also does the same thing. Good, no errors. Get status, get add all, clear, status. Okay, get commit some initial sketch of self play game. Initial sketch of self play game function. Initial sketch of self play game. It's just a sketch. It's like untested. It's just initial, and it's a sketch. Initial sketch of self play. I think you need like a hyphen self play game function. Initial sketch of self play game function, which is in train.ts, the new file. Get status, get push. So what's left is the whole sampling thing, like policy.sample move. Like that's what's left now. That's like the next thing to do. Commits initial sketch of self play game function. There's prob move. That's just trivial. Export function. We're just exporting. I already talked about this. Comment this whole sorting. Like who needs this comparator? Just this compare fn function. Let's just who cares about sorting it? Just policy is only like a wrapper just for this object, and also has these two new methods. One is the argmax move, like the move with like the highest probability, and the second one is sampling move, which is the next work to be done, which is the next order of business, which is to implement this sample move, which is, again, this is a leak code question, which I've done before, which kind of very easy to do. I guess it's a medium level, but it should be, well, whatever, medium level. And then train it is very surprising that just in that few lines, in just this many lines, we can self-play a game. I guess because that's what do MCTS, like it has all the hard work in there, like actually doing the Monte Carlo tree search. Like this line does a lot of heavy lifting right here. Line 19. Okay, yeah, I think that's good enough for now. Probably one of the shorter sessions, but yeah, it's getting late. So yeah,